Thank you for attending my presentation. This is Yunseong Cho, a fourth-year PhD candidate. Today's presentation is multi-cell coordinated per antenna power minimization for massive MIMO systems with low-resolution data converters. We have NC hexagonal cells with the base station in the center. Each base station has N-bit transmit antennas with low-resolution data converters, serving NU users. We assume sub-6 channel model with time division duplex. As a low-power solution, we deploy low-resolution data converters since power increases exponentially with the number of quantization bits. On top of that, multi-cell channels should be involved in designing communication functions. Also, there's a need to add an additional per antenna level constraint for a more realistic and power-efficient communication. Our objective is to obtain an optimal downlink precoder via minimization of maximum transmit power while satisfying target SINR. We begin with the downlink problem as our primary problem. Here, each antenna power is upper bounded by P0, which needs to be minimized. And this is the SINR constraint. However, this problem is very hard to solve directly. Therefore, we are going to transfer this problem into its dual domain. We found out that the dual of the downlink problem is the same as the uplink problem with uncertain noise covariance matrix D. We further proved that there's zero duality gap between these two problems. Inspired by strong duality, we get the optimal solution of the uplink subproblem for a fixed covariance matrix D. Capital lambda is diagonal matrix with Lagrangian multipliers from all users. We also derived the optimal downlink solution based on strong duality. Assuming that W equals square root of tau times F, tau is obtained when you satisfy the downlink constraints with equality. However, the optimal solution of the uplink problem is only for the uplink subproblem for a fixed covariance matrix. Therefore, we need to update the covariance matrix. Here, we are going to use the projective subgradient ascent method. First stage is to take a step into the positive subgradient. We further project the covariance matrix onto the feasible domain since the updated matrix is likely to violate the physical constraint. We finally have the iterative algorithm. Essentially, it summarizes the result that I have introduced so far. For an arbitrary initial point, we compute lambda iteratively. Using the converged optimal solution, we further compute the associated MMS equalizer, and then it gives us the optimal downlink solution. We also update the covariance matrix under further update is impossible. Let's move on to simulation results. We plot maximum transmit antenna power versus target SINR. We consider a network with 16 antennas, 4 cells, 2 users per cell, and 32 subcarriers. Dotted line, dashed line, and solid lines mean 2-bit, 3-bit, and infinite resolution. Here, black lines are from a conventional approach when minimizing total transmit power. Blue lines are from our approach that enables power-efficient communication systems. Blue lines achieve around 3 dB gain over black lines. Also, we can see that the performance gap by different quantization bits is very marginal because of proper formulation and coordination. On the right side, we have CDF of all transmit powers. This is for narrowband case. We can observe 2 main advantages from this figure. The first thing is the operating range. Blue CDF has clearly narrower operating range, which can enhance efficiency of power amplifiers. In addition, you can capture the gap between the rightmost points from 2 methods, which are the maximum transmit powers from each method. We also compare PAPR of both cases. Wideband case has about 4 dB gain, and narrowband case has around 3 dB gain. In conclusion, we designed beamforming through maximum transmit power minimization problem with low resolution data converters. For a better analysis, we proved duality and strong duality. We prove We proposed the iterative algorithm that solves both uplink and downlink cases based on strong duality. We further showed how to update the covariance metrics via projective subgradient ascent algorithm. Simulations validate the derived result for both narrowband and wideband cases. We have a list of related publications. Thank you for your attention.